Next up will be Ryan, and he'll be talking about Oreboot, a project I'm really excited about. Because you can see if you take some really good concepts of open source firmware and combine them with a really good fundamental part, the language, which is Rust in that case. So please give her a big round of applause for Ryan O'Leary.
Thank you, Julian. So today I'm going to present Oreboot. So I worked on it in the last few months with Ron, with Don, with Prachi, with Chris from Google. And also want to thank Andres Victor from the Rust Embedded Working Group. They have some excellent people there trying to make Rust easier to use in firmware, as well as Troy Ben-Jadigaris from the Sci5, who really helped us get Oreboot to work on the High 5 Unleashed board. So in this talk, I'm going to discuss what Oreboot is, why we chose Rust for this project, some of the design principles behind the project, how we got it to run in QEMU on the AST2500, the A-Speed board, as well as on hardware on the High 5 Unleashed board, as well as how you can get involved in the project. So there's us working on Oreboot, trying to get to work on some hardware. So yeah, first I'm going to go over what is Oreboot. So Oreboot is essentially Coreboot without C, so I'll give you a moment to appreciate this pun. So it's a downstream fork of Coreboot, which makes it open source and GPL v2. It's completely written in Rust. There's not a line of C code. There's a bit of assembly because you need a bit of assembly to initialize like the very low level CPU and initialize the stack pointer and stuff, but very little assembly. And the main aim is to jump to the kernel as quickly as possible. So this is sort of like the Linux boot model. We don't want the firmware to have any disk drivers or have like a network stack or debug shell. We want to punt all that into Linux boot because Linux already has an excellent network stack, excellent drivers, very high performance, and we don't want to re-implement it all. And the policy we really want to do going forward is to only accept fully open source components in this project. So for example, we wouldn't want any closed source blobs like FSP, and we want all the data sheets for the project to be open source. Sorry, not open source, but be able to view them publicly without an NDA. So here's a basic boot flow of Oreboot, and this is very similar to Coreboot. So we start with what we call the boot blob. It's not a single block, it's a blob of code. And this is mostly assembly. It executes directly out of SPI. It's the first instruction in firmware. It does the simple tasks like initializing the CPU, printing a welcome message. So in case it crashes later, you knew something happened at least. Sets up the SRAM or caches RAM, and then it finds and it jumps to the realm stage. So the realm stage mainly has one purpose. So at this point, you can't start Linux yet because your machine hasn't initialized the main memory. You only have about 30 kilobytes, so to like a few megabytes of SRAM or caches RAM. So at this point, the code just initializes the RAM or the DDR controller. So once that's done, we go to what we call the payloader stage. So this is a bit different from the RAM stage in Coreboot. The payloader stage has one purpose. It is to run the payload, and it doesn't do anything else. So there's no shell, no USB stack, no storage drivers, no nothing else. It just loads the payload and jumps to it. So that's why we called it the payloader stage, to prevent other other things from getting in. Then finally, you usually jump to a kernel such as Linux, which performs the job of Linux boot, which has a netramfs, which either fetches the next kernel from the network or loads from disk, etc. And one other goal of Oreboot is we want to focus on performant boot. So the holy grail of firmware is to be able to boot a machine in less than a second. As you probably noticed, machines nowadays get slower and slower. So like your laptop or desktop may take a few minutes to boot. Servers could take like up to 10 minutes. BMCs could take a few minutes, but it doesn't have to be this way. And there's many counterpoints, like Chromebooks boot quickly. Servers from like a decade or two ago booted quickly. Like where there's requirements such as in automobiles to boot quickly, machines can boot quickly. It's definitely possible. But there are a few pain points, like memory training takes time. Oftentimes drivers aren't run concurrently, which slows down the boot process, and a few other things. So our main goal is to be able to boot the Hi5 processor, which is Linux capable, into Linux in less than a second. So now I'm going to talk about why we chose to use REST and why we didn't want to use C. And this is kind of similar to the discussion which happened, I guess, 2 decades ago of why do you want to use C? Why can't we use assembly in our firmware? And the main reason to use REST is because it's a more modern language. It's a language which was created in the last decade. And you have many features to show, many features which benefit the productivity, the quality of the code, the reliability, the security. So for example, we have the borrow checker. I don't know, how many of you are you familiar with REST here? Oh, quite a few. It's really good. So we have namespaces. You don't need linker sets, I can see. You have hygienic macros. You have type-safe printfs. You don't have to care about inlining code as much. You have a standard package manager. You have REST format, and on and on and on. So I'll go over each one of these briefly. So the core principle of the borrow checker, and reading this sentence in the REST programming language book really enlightened me. The core principle of the borrow checker is at any given time, you can have either one mutable reference or any number of immutable references. References must always be valid. So REST doesn't really have pointers. Instead, you have an owner of data, and then you have references to it. And you can have multiple immutable references to that data, or you can have one mutable reference to it. So here's an example of C code, which is really bad. There's multiple problems here. So one is, well, you're casting from an int pointer to a void pointer, which is generally a bad idea. But the bigger problem is there's no guarantee that what X points to will outlive Y. So your static Y variable might outlive the thing it's being pointed to. So this is legal C. It's very bad. It's not possible to do something this bad in REST unless you use unsafe keyword. REST will greatly increase safety. And with the borrow checker, it provides more opportunities to the REST compiler to optimize your code. I'll have an example of using borrow checker in REST later. Another great feature of REST is namespaces. So in a lot of projects like Linux or Oreboot, you see that you have an ARC directory. And inside of your ARC directory, you have like RISC-V, you have ARM, you have x86. And in each one of these folders, you have an implementation of, for example, the hold function. So you have 3 functions with the same name. And when you compile that in C, generally you would have multiple functions with the same name error in your linker. And the way they work around this in C is mostly hacks. So you have if-defs, you have weak symbols, you have some magic in your makefiles. Sometimes you have pointers. But in REST, you have a very simple mechanism called namespaces, where you simply put each hold function into its own respective namespace. And then when you import it, you could rename the namespace to architecture, and you don't have to have any of these silly hacks. Another great thing about REST is it pretty much alleviates the need for linker sets, if you know what that is, which is a very good thing. It also makes the makefiles a lot less crazy. So this is an example of part of the makefile in Oreboot. There's a lot going on here, but you can see that it does get messy. In REST, you have this tool called Cargo, which essentially like figures out the dependencies for you and has a much simpler language than this. Another great thing about REST over C is it has what they call hygienic macros. In C, macro expansion happens just after tokenization, but before the parsing stage in the compiler. So you could have strange things like this, where your macro accidentally captures an identifier from outside the macro, or something would happens, or like in this example, there should be more parentheses around the identifiers. An example of this is the format args function in Rust, where you can, the formatting happens at compile time using a hygienic macro. This example here, the exclamation mark indicates that's a macro. The 2 curly brackets indicate where the formatted arguments go. So the first string goes into the first curly bracket, the 7 goes into the second one. You don't have to think about, should I use a %d, or should I use a %lu, or should I use a %llu? At compile time, it automatically figures out the types. If you put too many arguments, it's a compile time error. If you have an argument which you can't print, it's a compile time error. In C, it's like, that's like, you can have mistakes like that. We cast the 5 to a car pointer, and this is completely undefined behavior. There's the compiler usually doesn't check that. In some compilers you have warnings, but it's undefined behavior. Here's another example in C of undefined behavior. It's kind of difficult to tell, but that buffer, there's no guarantee that this buffer is initialized to a value. It actually depends on the implementation of VAS print. In some standard libraries, it might initialize it to a valid value, in some it might not. So this is solved in Rust because you can't have a reference to something that is not valid. Need for inlining. Oh, another great thing is Rust format. In many C projects, you might find different developers argue over tabs versus spaces or comment styles. In Rust, there is one way, which is you run Rust format on your code, and you just don't talk about it anymore. And Rust format also has also simplifies the code here. So you can see, so this is a diff before and after running Rust format, and you can see it removes this empty generic thing. This simplifies the code. It wasn't needed. It's quite nice. So now I'm going to go over the design principles behind Oreboot. We have this thing called the driver model. And we're still debating whether or not this is the correct model, but we find it quite useful so far. So essentially what a trait is in Rust, a trait is kind of like an interface. And you implement this interface by implementing the 4 functions. You have an init, you have a read, a write, and a shutdown. So we call it pread, it's positional read. The second argument is the position, the same as prewrite. When you read, you pass in a mutable buffer. So a reference to a mutable buffer. The read function fills in the buffer with data from the driver, and it returns a result type. So result type in Rust is either a number. So in this case, it would be usize, a number, or it's an error. And the error, as you see up here, is a string. So all our error codes are strings, which you can print and are human readable. So we kind of, this driver is kind of, it can be used for like what you'd call block devices or car devices, since you could ignore, the driver could ignore the position, like the offset, and it behaves kind of like a car device, or it could be used as kind of a block device as well. So here's some examples of the drivers we implemented. So we have what we call physical drivers, which are backed by actual devices and hardware. So we have memory, which reads and writes to memory. We have a couple serial drivers. They read and write to serial devices. We have clock, DDR. They initialize the clock and DDR respectively. Then what we have are these useful things called virtual drivers. So these ones aren't backed by actual hardware, but they still implement the driver interface. So we have union. This one's very useful. And you sort of, it's useful in the sense that if you have multiple UART drivers in the machine, so for example, if you have UART 0, UART 1, you can create a union of them. And whenever you perform a write to the union driver, it pushes the characters to both of the UARTs. So it's kind of like a fork. I'll explain it more in the next slide. Then we have a slice reader. So if you're not familiar, a slice is kind of like an array in Rust. And essentially, this driver just reads from a pre-filled in slice. This is useful in testing, as well as a section reader. This one's particularly useful. So for example, if you have a SPI device, which reads from like just say, for example, your SPI is 32 megabytes, but you kind of want to have a driver which is a partition of that SPI device. You can initialize a slide reader with the offset and size, so that driver can only read from that small partition of the SPI driver. And we use the section reader for multiple things. It's pretty nice. So yeah, here's an example where we create a console with multiple UARTs. So this was on the AST 2500, and they had 5 UARTs. So we kind of wanted to write to all the UARTs at once. We created an array of them. We created the union driver using this array. We initialized it when we do an init. It inits all the drivers, all 5 of them. We do a p-write. So we write to it. It doesn't matter what the position we write to it, because it's kind of like a car device. And you write to it, it writes welcome to Oreboot to all the UARTs. And then down here, we showed the example of using the like the res printf, the macro, the format args, and we kind of write the formatted output 7 to that console. So we essentially get printf for free here. It's easy to add and configure new drivers. We don't have to re-implement printf like every other C project in existence. So here's an example. So with that in mind, here's an example of the borrow checker and where it saved us. So in this example, we initialize UART, we init UART, we write A to UART, and that's all fine. Then we tried to initialize the clocks. So if you see down there, the line with clock new, that creates a new clock driver, and then we have p-write on to the clock driver, and that turns on the clocks. But when you turn on the clocks, you have to update the divider in the UART. Otherwise, the UART will be much faster than expected. So first you decrease the divider in UART, then you turn on the clocks, so that the UART has that constant 115.200 baud rate. So we pass in all the drivers into the clock, and it flushes UART drivers before changing the speed such that you don't lose any characters. So in this case, we're essentially passing the clock driver is taking a mutable reference to the UART driver we initialized here. And it's using this reference. So we initialize a new clock driver, and it's using this reference on this line inside the p-write function. But since the clock driver has a reference, we can't also p-write to it here. But we can p-write afterwards, because the clock driver is no longer borrowing the reference to the UART driver. And this might seem complicated. And you can see here's the error message here. The error message is actually quite useful. It says the line where the first mutable borrow occurs, and the line where it's later captured, and as well as where the second mutable reference occurs. And so it's good to remember this quote. At any given time, you can have either one mutable reference or any number of mutable references. References must always be valid. So that breaks the first rule. So this is how we lay out Flash in Oreboot. The Flash on the Hi5 processor where we tested this has 32 megabytes, which is much more than we need. So we kind of had large partitions, much larger than we needed. So the boot blob, which is the initial assembly, jumps down to the ROM payload. And this is the A and B partition, and then we have the RAM payload A and B partition. We invented this thing called a device tree file system. So we store all the information in essentially a device tree. It's kind of an abuse of what you might think of device trees, like a list of devices. Essentially, it's a list of files stored in a device tree to be used as if it were a file system. And the reason we found this convenient is originally we were planning to use CBFS. And to be able to access the files from Linux in CBFS, we were originally planning to write a kind of a fused file system to read CBFS from Linux. But we found if we just used DT, like device trees, we can pass the device tree into Linux through the typical means, and the device tree would appear under sys firmware dt. So all the files that you'd have access to in firmware, you can pass to the kernel through this interface. So for example, if you wanted to store for example, a splash screen that you want to display in Linux, you store in the DTFS externally to Linux, and it will automatically appear in sys firmware dt. It's kind of an abuse of semantics, because device tree is supposed to be for devices, but you can also store files in it, which we found quite nice. So currently, Oreboot is only 31 kilobytes, which is very small. It's about 1,000 times smaller than the flash part. So this is an example of how, like, the device tree file system, you can see the files that we store in it, and like how we mapped that previous description of the areas to a device tree format. This is kind of how our build system. So currently we use what they call the cargo make extension to cargo. So we still have these make files, but they're in a TOML format. We're trying to avoid kconfig, but it seems like we'll have to come up with a similar system because it's a bit difficult to like configure stuff by directly editing the make files at this time. Here's an example of the source organization. It's very similar to Oreboot. It's based off of Oreboot. We have the main boards. Inside each main board, we have a vendor, and then we have the individual boards inside the vendor directory. We have socks, which the main board usually imports the sock, and the sock imports the drivers, so the main board imports the drivers directly. Payloads is outside of the source directory, because you could build a payload externally to building Oreboot and add the payload later. Another useful property of REST is there's no dynamic, you could use it without any dynamic allocation. It's very easy to stack allocate everything. And REST has a tool you can use with the LLVM compiler to tell you how large your stack size is. So at compile time, you can prove that you won't have a stack overflow, because the compiler told you how big a stack is. You make sure you allocate that much space, and then you don't really have to worry about there being a stack overflow. Something else we want to implement is coroutines. So this code again is useful here. At any given time, you can either have one mutable reference or any number of immutable references. References must always be valid, which is very similar to databases in REST. Sorry, databases in computer science. So you have a database when you have two things relating to the same object at the same time in memory. In REST, that's not possible because you can't have two mutable references to the same thing, which sort of, in a way, makes REST memory safe as long as you don't use the unsafe keyword. This is something we've not implemented yet, but it's something that we will need if you want to have our the holy grail of firmware, which is 1 second boots. So we'd have a separate coroutine for UART, separate one for SPY. They'd be polling on being ready for new data, and at each cycle of the poll, they would yield the scheduler, the round robin, everything that was yielding to it. It's fairly simple, but we still need help to implement this. So, okay, so finally, running on hardware. So our first target was QEMU system ARM. This demo is very short. We only did this one in QEMU. So you see here when you run it, okay, CD to the right directory. Let's see if we can speed this up. CD mainboards, emulation, QEMU. We have this convenience function in a makefile, which is cargo make run, and it just runs it for you in QEMU. So you can see here, what we did was it went by kind of fast. But you can see it printed out the device tree, then boot Linux, it jumped to uroot, and then inside the uroot shell, I listed some directories. So this was relatively simple, but this was only in QEMU. When we went to port it from QEMU into hardware, we had some difficulty because the datasheet was NDA. So we didn't have access to the datasheet, which made the porting kind of difficult. So instead, we jumped to VISC-V. So this is a Hi5 unleashed board. It has a Sci5 FU540 processor. It has one management processor, and it has 4 processors which are capable of running Linux. It has 8 GB of DDR4. It has 32 megabytes of flash. Has SPI, UART, pretty much everything you want. It's very convenient to program. The architecture is a bit different from ARM. So you can see here, the boot blob runs from, so the code starts on the management core. You initialize the CPU, set up the car, then you jump to the realm stage where you print the UART message, initialize the clocks in the PRCI, which is the power reset clock interrupts unit. You initialize the DDR. So until DDR is initialized, use the caches RAM in the L2 cache. It's fairly simple to initialize DDR. And then you copy the payload from SPI into RAM, and you jump to it, and the payload is Linux. So the way we programmed this was with the dediprog. You have to make sure these MCell bits are in the right positions. And in this position, it jumps over the FSBL and the BBL, and it goes right to Oreboot. So we skipped the existing bootloaders on the system. The boot blob is very small, so this is all the assembly we have in Oreboot. It's like 1, 2, 3, 4, 5 lines. So we initialize caches RAM. Currently we spin all the CPUs except for CPU 0. We want to implement SMP in the future, but currently we're only booting 1 CPU, and then we jump to the start. The realm stage is some simple UART prints. Then we initialize the clocks. And you see, this is the first time we initialize the clocks. We made the mistake where UART is running at this baud rate, and the UART is a clock divider on the core clock. And once we initialize the clocks, it jumped to like 50 times faster than the expected baud rate. So that shows you first have to drop the clock divider, then initialize UART. The memory unit was fairly simple. Essentially, it's code which copies. There's like 1,000 control registers. You just copy them into the memory mapped address. We use the FSBL and the Coreboot implementations as reference. It's pretty much a direct C to REST translation of the code. It was only a few days of work, which is fairly easy. Our eventual goal is to boot the kernel in M mode. So currently we're using this patch, the no MMU patch from Christoph Hellwig, and this lets us boot the kernel in M mode in QEMU. It currently does not support actual hardware. That's hopefully something we want to work on the hackathon this week. It's a very exciting project. So if you don't know, M mode is kind of the SMM mode of VISC-V. But we want to run the kernel in this M mode. OK, so this is how you can get involved. So we have a discussion, a Slack here, the Oreboot channel on the root Slack. We have GitHub. There's a bunch of bugs you could look at. If you're kind of new to Rust and you want to learn about Rust, I highly recommend this online book. The way I learned Rust is you go through every single chapter. You look at the code in every chapter. You type it out by hand. Make sure it compiles. Try flipping around some lines in the code to see how the borrow checker reacts. It takes a bit of time to learn, but it's definitely worth it. If you want to learn VISC-V, I highly recommend this book. It's a short 130 pages, but it describes the entire VISC-V architecture, which is very short for a whole architecture. And then we have there's a bunch of tasks we kind of want help with. And we'll probably be working on some of these in the hackathon this week. So if you want to drop by and experience what it is like to work on Oreboot, please feel free. And that's it. Any questions?
Thank you, Ryan. Let's have another round of applause for Ryan. And you're exactly on time. So we have time for about 10 questions. Yeah, just go up to the microphones and ask your questions. Just line up. Yeah.
You said something about no NDAs, but one of your supported target is the A-Speed, which does not have a non-NDA manual.
Yeah, and that's the reason we moved away from the A-Speed and worked on the Hi5 processor.
So are you planning to remove it until A-Speed gives you an open manual, or?
It's pretty much removed at this time. So you can still find the source code there in a directory, but it likely doesn't compile because we removed it from our CI system and no one really tests it. So feel free to send a patch to remove it.
I'd be interested how the code size looks with Rust. Because, for example, you said that you essentially get a printf for free, right? But you don't really get it for free. You get it by dragging in a giant standard library. So
yeah. So currently, all the Oreboot code that we use to boot, actually in QEMU, we use it. So we use the same Oreboot binary for QEMU and on hardware, which is kind of nice because you could test in QEMU, you could take the same one, test on hardware. To boot Linux in QEMU, it's only 31 kilobytes, and that's including the printf statement. So it's very small. I'm pretty impressed by the LLVM compiler. We use what they call link time optimizations, which is really able to remove a lot of code. It's kind of inlining, but between different modules in the code is very, very, very good.
But have you done something like take about the same amount of code, like the same driver or something from Coreboot and Oreboot and compare?
We haven't really done that comparison yet, no.
How do you boot the same Oreboot on QEMU and hardware?
So essentially what we have is, it's kind of a hack, but we have these isQEMU functions. So if it is not QEMU, we skip.
How do you know it's QEMU?
There's actually a few ways of telling. What we do right now is we look at this register in the mask ROM, and on QEMU, we know it should be this value. And on hardware, we know it's that value. And they kind of differ in the implementations. So in the future, QEMU might look more like hardware, in which case we kind of have to change our isQEMU function. But for now, it works.
All right, so what's the plan for running on the Hi5 Unleashed in QEMU? The model of the Unleashed in QEMU?
Yeah, so right now, the machine type we're using QEMU is the sci5_u. We had to make a few patches to that to make it look more like hardware. So for example, QEMU loads the firmware at the offset 0x8 with 7 zeros, when hardware it loads it at 0x2 with 7 zeros. So we had to make some patches in QEMU to add that section and load into different place. But for the most part, the code is very similar.
Oh, okay. So you're running the sci5u though, not the
yeah,
machine. Okay.
That's right.
I have another question. We'll come back.
Why do you have to initialize the UART and then adjust the clocks? Why you don't do it before you initialize the UART or during the initialization?
Oh, because we want some prints to happen before we initialize the clocks, and we want some prints to happen afterwards. But since the UART, they use the same clock source. They use the clock source, the same one as the CPU. So the CPU clock source, by default, it runs at 33 megahertz. And then when we initialize the PLL, it jumps to, I think, 1 gigahertz. And since the UI is a clock divider on that clock, you kind of have to change the divider at some point.
Okay. So you want to see some UARTs for debugging before you bump the...
Yeah, that's right.
Okay. And I have another question. Would Rust will be a good potential to replace other usage of C, or it's only kind of targeted to bootloader BIOS and
it's definitely used elsewhere. It's actually, from my understanding, Rust was originally created by Mozilla to be used in their web browser because they have a lot of, I think it's web layout. I'm not too familiar with the field, but they want to lay out their web pages, but concurrently, and it's very difficult to do safely in C++. So they wanted to port that to a safer language, but one didn't exist, which was efficient. So they created Rust for the task. But it was also found that Rust was also very useful for bootloaders or firmware in general. So it's kind of the other way around. First it was used in other fields, and then it moved to firmware.
Okay, thank you.
Another question. Why M-mode Linux?
Oh, why? I think the so I guess the idea behind this is like we're from a mostly x86 background, our team, and we have this aversion to SMM mode. And seeing M mode on RISC-V, we sort of had the same aversion. And we feel that we can sort of solve this problem by running the kernel in M mode in the most privileged mode. And then there won't be anything below the kernel which interferes with it.
That's nice, but then there's no MMU, right? So
Yeah.
and no hypervisor support, and I mean,
Yeah.
okay, that's fine.
MMU free Unix is actually fairly old. In kernel mode, it's fairly old.
Yeah.
You don't need an MMU in the kernel.
Yeah.
Goes back to the first bit. So yeah.
But there's more than that, right? Hypervisors don't work. Then if you're running in M mode, your other future things, you're going to run into lots of issues.
Just wanted to add one
Yeah.
point. So no MMU mode, the no MMU port, the patches and you pointed out.
Yep.
So it does work on the CanWrite board hardware.
Yeah. Yeah.
You can
That's
try
what I've
that.
heard.
So you said no hardware supported. So
Oh, yeah, that's true. So yeah.
you can try the CanWrite.
Yeah, corrections. Yeah, so it works on the it's the K210, but doesn't work on High-5 at the moment. But I think our main goal is to get it to work on the High-5 this week.
Rust is a relatively young language. This is the first project I've heard of that uses it for firmware. Were there any challenges in making it work in embedded development?
Actually, it's fairly easy. I think most of the work has already been done to get it to work for firmware. Albeit we actually do use the nightly version of Rust. You can't do any of this in the stable version. But the working group for firmware for Rust has done a really good job, like setting up all the tools and making them easily accessible. There are a few tutorials you could find online to set up your tool chain to build Rust for firmware.
So I had another question. You mentioned there's no blobs, but
Yeah.
then you said to initialize memory, you just copy like 2 kilobytes or whatever, 10 kilobytes of something into registers.
Yeah.
That's a blob actually, isn't it?
Yeah. So I guess it's yeah, there's some semantics behind it, but so like it's not, the blob isn't executable code. It's like a bunch of register configurations specific to this board. It is true that we don't necessarily know what all these control registers do, but at least it's not like executable code that we don't know what it does. But still, you do have a good point. As far as I know at the moment, there aren't, as far as DDR controllers go, it's very hard to find one which is actually fully open source.
I just wanted to mention, apropos the tooling, I laid out the first RISC-V sort of structure, and then I did a cargo make and watched the thing say, oh, looks like you need the RISC-V version of Rust. Okay, pulling it down, done. A few seconds later. For anyone who's ever been through the hell of cross GCC building, it was quite a miracle to watch it happen.
Yeah, the tooling is fairly excellent. So like, for example, with cargo, you just type cargo object dump, and it does an object dump. And you don't have to care if it's RISC-V or ARM or whatever. You just type cargo object dump, and it figures out the architecture for you and dumps the assembly code. It's quite nice. So like if you compare that to GCC, where you have your RISC-V GCC toolchain and your ARM GCC toolchain, you have to make sure you have the right one, and you have to pass in the right arguments and everything. It's very nice.
So
Last question.
it sounds like you're not doing memory training. Are you planning to do memory training? Because all those magic numbers you're copying probably have to change based on variations in the board to reach maximum memory performance.
Yeah, that's probably true. So we're using the values of the control registers specific to the High-5 board at this time. But performing actual memory training should be fairly similar, I believe. I'm not too experienced though.
Okay, thank you, Ryan. Please give another round of applause.